Hey there. I've gotten some questions recently about Damascus steel, also known as pattern welded steel. I wanted to cover a few quick parts of that, and hopefully we can kind of have a dialogue in conversations and these videos to try to address all your questions. So, first item, obviously, I've just got drawn up here normal stack you might start with when making Damascus steel. We'll just kind of assume for the case of this video that we're going to be working with, say, 1080 and 15N20. This is a really nice combination, really common, fairly easy to get steels. So now, a lot of you might be familiar with what we refer to as atmospheric welding, sometimes also called dry welding. And essentially, this is the process of welding all these layers together without the use of flux, without the use of a can around it. Really just, put it in the forge, heat it up, smash those layers together. It works amazingly well, and I would argue it is in fact the only type of welding there is that in a certain, at least in terms of forge welding, that in fact all other types of welding are running on the exact same chemistry, and that's why dry welding works so well, and why, in some sense, we're all so surprised by that. It works great, and because of other things we've been told over the years, we don't expect it to. So, what keeps a billet, or what prevents a billet from welding? Essentially, if you have oxides in between your layers, those oxides will prevent the billet from welding. The higher the chromium content and the higher the nickel content of your materials, the harder it's going to be to get that weld to happen, because both nickel and chromium have very persistent oxides. This is why stainless Damascus, which we're not covering today, but it's why stainless Damascus is so much more difficult than normal carbon steel Damascus. So if we have these oxides in between, how do we get rid of them? For years we were told that in order to get rid of those oxides, you needed to get flux in there. And not only did you have to get flux in there, but then you had to somehow miraculously get the flux out of there. And a talk that I saw by Daryl Meyer talking about flux welding. This is probably 2 decades ago at this point. Clearly when I was just a toddler, because I'm so young. He pointed out that if you have, let's take your atom of flux, not that you can have an atom of flux, but your molecule of flux, your little particle of flux in here. Now, when you smash these layers together, it is in fact physically impossible for a particle in the center to be ejected. The amount of distance that is being closed to squeeze it out versus the amount of distance it has to travel, it becomes a physical impossibility. Your little particle of flux would have to exceed the speed of light. It basically accelerates to infinity, and that's impossible. So, right from the beginning, people knew, or I shouldn't say the beginning, but for a long time, people have known that flux welding had this, desperate problem of having trapped flux. That, it got in there, it cleaned all the surfaces, but it had this problem that it was hard to get back out. At the same time, if you look at something like wire rope, a cable, and making cable Damascus, if you think about it in those terms, it becomes, in terms of that flux getting out, it becomes kind of miraculous that the flux could ever possibly get out of there. And, those of you who have done cable Damascus using flux, you may have ended up with nasty black inclusions in there. I know when I've done cable Damascus, that's been a problem for me. And it's because the flux gets in there, it's basically impossible to get it back out. You can kind of squeeze it to one end, but even so, it's essentially impossible. So, how does dry welding work? We're going to cover that quickly, then I'll come back to the flux for a second. So dry welding depends on the carbon that is already in your steel. So as you get to elevated temperatures, carbon starts moving around. You get higher mobility, carbon diffusion, I'm sure you've all heard about. So as that carbon becomes more mobile, it is also available to come to the surface and react with the oxides on the surface, break those oxides down. So you've got iron oxide, we'll just say it's FeO. There's a bunch of them, but we'll just call it FeO in this case. One carbon molecule or one carbon atom comes to the surface, FeO breaks down, you get pure iron, and carbon monoxide floats away as a gas. And this is part of why the hotter your steel is, for the most part, the easier it is to weld. The hotter it gets, obviously it's softer, but also carbon migration becomes exponentially faster as you move your temperature up. So it becomes much easier for carbon to make its way to the surface. Because of course, if we're doing atmospheric welding, the dry welding, we're not welding up all these seams on the sides. We're not arc welding those or anything. They are not sealed. So theoretically, you can continue to get oxidation along the edges, no matter what your forge environment is not perfect. Even if you tune it down so that you've got a gas-rich environment in there, even in that situation, you still almost certainly have free oxygen floating around just because your burn's not going to be perfect. So if you've got oxidation happening on the outside and to some degree making its way in, the hotter your steel is, the faster carbon is coming to the surface. And what that does is not only does it react with the gas, sorry about the furnace noises, not only does it react with the oxides on the surface, creating that carbon monoxide gas, but now you're creating pressure between the layers. You have positive pressure of that gas floating out, keeping oxygen from penetrating, keeping that forge atmosphere from penetrating between the layers. So your steel cleans itself. This is also why lower carbon materials, generally speaking, need higher welding temperatures. If you have less carbon available, you need to really push that temperature up. There may be some other factors involved there, but we'll get into that maybe another time. But going back to the flux for a minute, those of you who have used flux on a billet know that when you put your billet into the forge, it's got moderately hot, you put some flux on it, and it melts on kind of like honey. And that's sort of the sign that things are moving in the right direction. It melts out onto the surface, it coats beautifully, and then the sign that it's working is that you start to get those little dancing bubbles. Particularly, some everywhere, but particularly at the junction of the layers, at these seams. Now, what we've always been told was that shows that the flux is active. I don't think that's true. I think what you're seeing is the carbon monoxide bubbling out. So if you use, if any of you have done any jewelry work and you use flux on, say, copper, and the copper flux is very closely related to the flux we would use in forge welding. Copper flux, those are typically like boric acid, whereas we are using borax. They're chemically pretty close, and they function in very similar ways. And it's not to say that they don't dissolve oxides. I think there's pretty good evidence. If you put borax onto a piece of steel, you can see it helps clean the steel. It does do that. However, that bubbling action is not the flux cleaning the steel. If you just put borax on a piece of steel and start heating it up, it will melt on, and you'll just see the surface clarify. There's no crazy action involved in that. And the same is true, like I was saying, in jewelry work. When you use flux, sure, it bubbles at first, but that's water vapor coming out. But when it's actually working, well, I shouldn't put quotes on that. When it is working, it's totally still on the surface, and you just watch this. You watch your silver or copper become clean under the flame. So, going back to this, if you do flux the surface of your billet, really what you're aiming to do is not get the flux in between. If anything, you want to make sure the flux doesn't get in between. But instead, it's a coating. It's much more like what the Japanese would do with their clay coatings. Those clay coatings create an encapsulated atmosphere and help the steel clean itself. The steel is always fighting against the forge atmosphere, so if you can set up a situation where it's easier for the steel to clean itself, that's great. You'll get better welds. Lots of people do the same thing. They will, either they will weld all their seams, not entirely necessary, but effective. Or for that matter, people will put a box around this, put it in a piece of steel tubing, or wrap it in a sheet of some kind. All these things work. They're not changing the underlying process. The underlying process is that the carbon in the steel cleans oxides off the steel. So another point worth making here is that this process of carbon combining with the oxide on the surface and floating away is happening all the time while your steel is in the forge. You're probably all familiar with the idea of the decarb layer. Well, that's what causes it. You have iron oxide on the surface. Carbon is constantly coming to the surface, combining with that iron oxide, floating away as either carbon monoxide or carbon dioxide. Another point here that I should make is that the normal tight oxides that you would have on steel straight from the mill, maybe not hot rolled steel, but cold rolled steel certainly, and to a degree hot rolled steel. Those are tightly adhered to the surface, so you could say that they are chemically continuous. Therefore, carbon migrating out of the steel can reach those oxides and they float away. However, loose oxides that have become separate from the surface, or where you have such a thick layer that really, carbon's going to make it to that first layer, not really easily make it through. Those oxides are not going to be readily broken down by this process. Certainly carbon or oxide that is not attached to the surface, how's the carbon get to it? Can't do it. So therefore, like when we're doing a Damascus stack, we just take those mill pieces, throw them together in a stack, have it pretty tight, and we don't worry about cleaning it. When we are re-welding, when we're restacking, we always grind those surfaces fairly clean. You don't have to take off every single tiny little dark spot. You certainly can, but you don't have to. What you want to make sure you get rid of is all of that loose material. I know some smiths actually sandblast their steel to take off all the oxides. If you do that, you want to make sure that whatever your sandblasting media is, it is not leaving some kind of residue on the surface. Uh, Aluminum oxide, basically all the abrasives are going to leave some sort of residue that would prevent a good stick between those layers. So what I often suggest people do is if they're going to sandblast, that they then follow that up with running over a wire wheel. Make sure it's not a brass or brass-coated wire wheel. You don't want a layer of brass in there. But what that does is that will knock off any of that dusty residue. And just like with soldering in jewelry work, a very, that matte surface, that dry surface, it seems to be less conducive to bonding processes. Um, so, you may also want to know our process for atmospheric welding. And I can give a quick run through that. We will do a later video in which we actually show the whole process, but just as a quick primer on what we do. Let's say we're doing, a 2-inch wide, 3-inch tall, 6-inch long billet. We can do that. We've got a big hammer, presses, that kind of stuff. So we have the ability to set those welds and forge it out effectively. You need to size your billet to what you can work effectively, but the size of the billet matters less than the fact that it's appropriately scaled to how you work. So we'll take that stack. If there are any burrs or things on there, we'll grind those off. But like I said before, we don't actually really clean the layers at all. Stack these up, and then TIG weld the corners and typically down the center of each long side. If you don't put that extra weld in there, what will happen is as those outer layers heat up, they'll buckle away. That obviously creates big airspace in there. You get a lot more oxidation. Plus, it slows down heat transfer through the whole billet because you've opened up this airspace. So throwing those TIG welds down the side is really helpful in holding everything together. Throw it in the forge. Forge should already be fairly hot. You can have the two come up together to some degree, but you don't want to be starting from a cold forge with a cold billet because it'll just take a long time to heat up, and that whole time while it's heating up, you're going to be getting oxidation. The temperature of the billet needs to be fairly elevated before carbon migration to the surface is faster than oxidation by atmosphere. Putting your billet into a hot forge, depending on the size of the billet, might take 5 minutes to come up to temperature, might take 10 minutes, whatever it is. You really want this to come up to, a nice yellow. We're talking mostly, most of this welding should be done, 2200 degrees and hotter. Obviously, you don't want sparkling. You don't want to start burning your steel. But, within reason, hotter is better. once your billet is starting to get pretty hot, it's not a bad idea to pull it out and just squeeze those layers together tighter. In your initial stack, almost certainly you've got some airspace. Very likely you're going to develop more airspace during the heating process. Things will have expanded and buckled a little bit. So squeezing that all together tight really helps this chemistry work, just because it makes sure that there's nice close contact between the steel and any oxides you have. And also, the tighter these layers are together at this stage, the easier it is to develop that positive pressure of carbon monoxide or carbon dioxide pushing out and maintaining that positive pressure between the layers. At this stage, once the billet is at welding heat, that nice bright yellow, verging, not white, but getting towards that direction, we let it soak in the forge. Depending on who you talk to, depending on how clean your layers were, 5 to 10 minutes. It also depends a lot on the size of the billet. Larger billet, you'll want to let it sit a bit longer to make sure that temperature has really gotten all the way through. Once you've done that, 5 to 10 minute soak, bam, you put it together. It's a solid piece. What I like to do is, so I do that initial squeeze to make everything tight, do the 5 to 10 minute soak, set my welds, just do one round to set the welds, toss it back in there while it's still nice and hot, and give it another, 3 to 5 minutes soak, and then, really set everything final. And at that point, you should be able to just go hog wild with this material. It's going to be incredibly strong welds. The only thing you might get are some little seams at the outside. They are typically, if you're doing it right, they should be shallow enough that surface will actually flake off as scale pretty quickly. If you find that you're getting deeper seams at the outside and it's really becoming an issue, one thing you can do is after you've set your weld, flux the outside. That will give you that protective coating. This flux won't penetrate between the layers, but it will, it will help seal up these little seams, and you'll probably be able to get that last little bit of weld. Downside of doing this is, one, you've fluxed your billet, so you've also fluxed the inside of your forge. As all of us know, flux and forges don't get along well. And also, now you have introduced flux into the equation. It means that when you go to restack, you want to make sure you've absolutely cleaned all your surfaces. You don't want that old, sort of that compound of flux and iron oxide. You don't want it between your layers. The carbon coming to the surface is not capable of breaking down that compound effectively. So most inclusions are caused essentially by the flux. If you had left it as just a dry weld the whole way through, all you will ever have in there is iron oxide, and iron oxide is something that the steel can deal with itself. You give it the right opportunities. Okay, moving on. Okay, so we've got the basic chemistry of how forge welding works. Now, a little bit about the different types of Damascus that you might be making. So, really, still using our same diagram here, we've got this surface would essentially be most of the flat laminate patterns. You know, if you are revealing your pattern on this surface where you're maybe cutting through layers, either purposefully or just through creating a lot of layers, most of those we'll just refer to in later videos as flat laminates. And that's going to include ladder pattern, raindrop pattern, all the variations on, you know, creating a topography and, you know, cutting through the layers to reveal them. Edge grain, you don't really see much done with that other than in twist patterns. And we'll get to twist patterns in a minute. You know, I think edge grain might be a aspect of Damascus pattern development that will get played with a little bit more. But right now, the only real places you see that, see the edge grain used, are in pinstripe Damascus and serpentine pattern, which you sometimes see on certain types of like Viking blades, things like that. And so the other major portion you can use is the end grain. And this is where we get the mosaics. Obviously, anytime, you know, if you're doing a topographic pattern, a flat laminate pattern, you are cutting through and revealing the end grain. However, generally you're not really revealing it extensively enough for people to really think of it as being a mosaic. You can, however, develop a mosaic pattern, you know, really concentrating on what this end looks like, and then reveal it using, you know, some kind of a topographic or flat laminate technique. But, you know, this end grain, you know, how you reveal that changes greatly the effect you're going to get. You can, there's the fairy flip, where you're cutting on 45-degree angles and flipping those out and welding them together. There's just simply taking tiles and welding them edgewise. Typically, in that case, they're made fairly thick. They're not thin tiles. They get forged out thin, but they start fairly thick. Some folks will develop a bar and then just take slabs off the end, almost like cutting slices off of a loaf of bread. Let's see, another method pretty commonly used is an accordion, where you take cuts from either side through there and then open that out. Of these, probably the accordion is, you know, might be, depending on how you do it, the most material efficient. However, it's also the most fraught. It's the most likely to tear your pieces apart. So, you know, you might save on material or you might scrap the whole thing. That's why the accordion is, I think, becoming less common, while some of the other techniques are becoming more common. So, going back to twist pattern, which I said we would, fun thing about a twist pattern is that not only do you kind of play with seeing the flat laminations and the edge grain, but then as you cut more deeply into your twist, you begin to reveal that end grain as well, particularly kind of this outer third to each side. So there was actually a pretty strong tradition of doing what amounted to mosaic patterns in bars that were intended to be twisted. If you go back and look at particularly some of the German gun barrels, the Damascus gun barrels from, you know, the late 1800s, early 1900s, you see a lot of patterns that are essentially mosaic patterns. You wouldn't see the pattern, you know, in the edge or flat of your grain, But once twisted and cut through deeply, you would start to see this. They spelled out words, they made little star patterns, all kinds of stuff in there. So we will go into these different techniques a lot more deeply in future videos. But like I was saying, the basic breakdown is based on which part or which combination of parts of those laminations you're going to look at. And we'll talk a lot about things you might do. So rather than just a flat laminate, you've got something more more interesting going on. Crushed W's, other variations on mosaics, such that regardless of how you're revealing it, you can get something a little bit more exciting than just some wavy lines. So hope this helps some. Like I said before, if you have additional questions, make sure you post them. If there's something I haven't been clear about or you want more details, ask away. It's hard for us to know exactly what what things might not be making sense. Make sense to us, so clearly that means we did it right. Now, obviously the answer is you ask, we'll do our best to answer those questions. We really want to make sure everybody is as clear about these things as possible and therefore as successful in it as possible. Thanks for watching.